In a multi-step synthesis, one step after another, the time-consuming part is purification of each intermediate. Mixing up the reagents for a reaction doesn't take much time. Waiting for the reaction, usually not much time. But purifying your product from the excess reagents takes a long time. Solid phase synthesis is a huge time saver if it can be worked out so every step is very efficient. I've already talked about solid phase syntheses of nucleotides in a previous video. And that's so refined that you can just program a computer, tell it exactly what sequence to make, hit start, and a machine will add reagents, let them react, wash away excess reagents, and keep cycling through the process. The same applies to peptide synthesis. Throughout, the trick is excess reagents can be used to drive the reactions to completion. That gives you a high yield. You need that if you're going to do multi-step syntheses with no purification. And then those excess reagents can just be washed away because they don't become attached to the resin. Only the thing that reacts on the resin stays with the resin. The solid support is not dissolved by organic solvents. The reagents are, so they can be washed away in each cycle. There are lots of resins. Let me choose the basis for one of the original ones. This is styrene. There are many ways to polymerize styrene. And when we do, not surprisingly, we get polystyrene. Polystyrene, if it has the right chain length, is not soluble in organic solvents. Under the right conditions, we can make polystyrene as little b. If you make them in outer space, those beads come out beautifully spherical. Isn't that cool? But there's no functional group on polystyrene to attach anything to. So let's use a little trick here. If we put in this chloromethyl derivative of styrene, mix them up, and do a co-polymerization, then every so often a chloromethyl is introduced in the chain, and that gives us a handle to do something with. So now we have functionalized polystyrene, doesn't dissolve in solvents, and it's got that useful benzylic chloride. The next step is to add a linker. The linker is required for reasons which I'm keeping secret for just a little while. In this particular case that I'm thinking of, we'll add the linker by SN2. So typically something like a phenoxide, perhaps, doing a displacement of the chloride on that resin, and it will work beautifully because it's a benzylic chloride. A key characteristic of the linker is that the nitrogen protecting group is easily cleaved by base in the approach that we're following right now, and that's the FMOC approach, it's called. But at the end of the synthesis, the nitrogen will be cleaved from the linker, carrying everything that we've added to the nitrogen with it. The linker then has got orthogonal chemoreactivity. After we've added the linker, it's always with us. So let's not write it down over and over again. Let's abbreviate that solid phase resin with the linker on it to this blue symbol here. But you know the linker's there. I've told you it's just an abbreviation from here on. So let's take our resin and cleave that protecting group, P, with the base. I'm not telling you what the protecting group is yet, but you don't have to think very hard to know it's an FMOC protecting group. So now we have a free amino group on the resin, and we're ready to start the peptide synthesis. Peptide syntheses go via acylation reactions. So we take an amino acid, also with a protecting group on the N-terminus, and we couple the C-terminus to the amino group on the resin. How might we achieve that activation of an N-protected amino acid? Lots of ways, and many of them involve mixed anhydrides. And in this video, I went over mixed anhydride chemistry. So we could use a mixed anhydride with dicyclohexyl carbodiimide, for instance. If you're not familiar with that, please take a look at my previous video. So that activated carbonyl of the N-protected amino acid in solution used in excess is going to add to the nitrogen on the resin, a simple acylation reaction. In peptide synthesis, we call this a coupling. That amino acid is carrying a protecting group. And if it's an FMOC protecting group, it's base labile. So we can repeat, cleave off the protecting group and get a free N-terminus on the amino acid that's been added to the resin. So base-mediated deprotection and then coupling adds a second amino acid to the resin. If we deprotect and couple again, we get a tripeptide on the resin. And we can keep going for as many amino acids as we need, providing each step is very efficient. So for tetrapeptide, another deprotection and coupling, a pentapeptide on the resin. Let's say that's where we want to be. We want to make a pentapeptide. So now we pull in that other characteristic of the linker. Remember, the linker's there, but we haven't drawn it in. And remember, whatever's attached to the nitrogen on the resin will cleave when we cleave that nitrogen off. We cleave it with a strong acid, orthogonal to the base deprotection of the FMOC protecting group, and we get a peptide derivative in solution. It will be protonated on the N-terminus. The C-terminus is not acidic because it's a carboxamide in this case. We can arrange for the C-terminus to be an acid also. It's your choice when you make the linker. Simultaneously, there might be protecting groups on the side chains. Some amino acids, functionalized amino acids, often require protection so that the coupling goes smoothly. I won't talk about that in this video, but when we cleave from the resin, typically we cleave those side chain protecting groups. They could be based on Bock chemistry, for instance. That product is typically precipitated from ether and then dissolved up again and put on a reverse phase HPLC column. Of course, first, you would do an analytical HPLC to see the purity of your product. If it's good enough, then you would go to the prep column, use more solvent, more time to purify your final product. Let's look at that protecting group, which I've called P, and I've let you in on the secret. It's an FMOC protecting group. What does FMOC stand for? What's the structure of an FMOC protecting group? FMOC means fluorenyl methyl oxycarbonyl, and it has this structure. That system with two 6-membered rings and a 5-membered ring is a fluorenyl group. I've told you it's base labile. I wonder if you see how. Well, what could the base be? And typically in peptide synthesis, we use piperidine in the FMOC approach. It could be pyrrolidine on some machines these days, but piperidine is the classic one. What will piperidine do to an FMOC protecting group? It will deprotonate it on the fluorenyl CH. Why is that CH prone to deprotonation? It's because when we form a fluorenyl anion, that anion is stabilized because it's aromatic. 6 electrons in one ring, 6 electrons in another ring, that's 12. That's not an aromatic number. But 2 electrons more from forming that anion, and we have a 14 pi electron system. Aromatic. So the anion forms quite quickly. That's the fast step. And the second step is an elimination. an E1 elimination because it's first order. E1, first order, catalyzed by base. E1CB, deprotection of the phenyl group. And we get an alkene from the phenyl part, which we can easily wash away from the resin, and piperidinium, which also we can wash away, and CO2, I'm sorry, it just goes up into the atmosphere. On a tiny scale like this, it doesn't make much difference. What could the linker be? Well, I've been protecting you from this because the linker looks like a bit of a monster. This is a linker. This is actually the Rink amide linker. You see it has an FMOC group on it. A rookie error for people doing peptide synthesis for the first time is they typically forget to take off the FMOC group. And then, of course, the first coupling fails. If that FMOC group is deprotected, and we do cycles of coupling and deprotection, coupling, deprotection over and over again until we get to the sequence that we desire, then at the end of the reaction, note that that N terminus for the carboxamide is attached to the linker, and the linker is bisbenzylic. So if that carboxamide is protonated with an acid like trifluoroacetic acid, it protonates on the carbonyl, not on the nitrogen, remember, on the carbonyl because of resonance. And then the rest is easy. We form a bisbenzylic carbocation, and the carboxamide is liberated in solution. There's a lot more to peptide synthesis. I haven't told you anything about the protecting groups. I haven't told you about other methods like the more old-fashioned FMOC approach. That's got a big disadvantage relative to FMOC approach insofar as to cleave from the resin. Typically, you need HF, a very corrosive, unsafe reagent. Peptide synthesis is beautiful. If you're a life science major, it's good to know that you can make peptides in this way, but more often, if you're doing research or you're working for a biotech company, you just go to a service provider and ask them, please, make me this sequence, and they will make it by solid phase peptide synthesis and then HPLC purification. Thank you very much for watching. Good luck with your studies.